Assalamu alaikum. Yeah, thank you so much for having me. It's my pleasure that I can present my thesis topic with all of you. The topic of my thesis presentation is design and analysis of plasma temperature sensor utilizing photon-like crystal fiber. I'm Muhammad Kamal Hassan, 1510010, Department of Electrical and Computer Engineering at Russia University of Engineering and Technology. First of all, I thank my supervisor, MD Mahabur Ahmad Sir, lecturer, Department of Electrical and Computer Engineering, for helping me a lot to complete my thesis. This is the outline of my presentation. First, we discuss about the overview of SPF technology, then advantages and different types of SPF sensor, photonic crystal fiber, literature review, objectives, proposed model, simulation results, conclusion and feature, and references. Figure 1 shows the mechanism of sphere. When a polarized light hits the negative permitted material interface, then a free electron of a negative permitted material absorbs the photon energy from the incident light. This electron is known as surface polaritron. This polaritron, this SPPs create an oscillation. This oscillation generates the surface plasma wave. As a result, a sharp loss peak appears. Shift of sharp loss peak, shift of loss peak with changing the value of refractive index of analyte develop the repeated windows of the analytic after shifting the sharp loss peak. We can detect the environment change of the we can detect the environment change. The material, especially negative permitting material, is used for SPR phenomena because the negative permitting material has a much free electron that can absorb the photon energy of incident light. Gold and silver are the most commonly used. Silver for using silver we get a sharp loss peak, but silver is easily oxidized, and gold is free from oxidation. That's why gold is mostly used in SPR phenomena. Application of SPR-based sensor, medical diagnostic, bioimaging, environmental monitoring, telemedicine, chemical sensing, glucose monitoring, and disease detection. Advantage of SPR: advanced identify level-free molecules, high sensitivity, real-time reaction monitoring, and specific and non-specific absorption and fast response. There are different types. There are mainly two types of SPL sensor can be available. One is prism SPL sensor, then another is fiber SPL sensor. Fiber SPL sensor, photonic crystal fiber is most promising of sensor. Photonic crystal fiber based sensor is most used in recent days. Prism SPL sensor. This figure 3 shows the prism-based sphere sensor. This sensor is widely used, but there are some limitation on prism-based sphere sensor. One is a bulky size and limited in remote sensing application and limited analysis throughput. Overcome the limitation of sphere-based sensor. Researcher introduced a PCB-based sphere sensor. In PCF-based sphere sensor, PCF consists of a periodic micron size of air holes. Holes can be arranged by circularly, hexagonally, and octagonally. Properties of a PCB space sensor can be altered by changing the structure like size of air holes, thickness of sensing line, etc. The figure show the development of PCB space sensor. The detection technique. And there are two types of detection available. One is angular interrogation technique and another one is wavelength and amplitude interrogation technique. Angular interrogation technique is mainly used in a prism-based space sensor, and wavelength and amplitude interrogation technique is used in PCB-based space sensor. Advantage of PCB-based sensor: increasing sensitivity, more tunable, less complex fabrication, and remote sensing application. That's why I propose a temperature sensor using PCB-based technique. Literature review. In this literature review, in Abed et al. Proposed a temperature sensor with sensitivity in 1.96 nanometer per degree Celsius. He used silver as a plasmonic material. Figure 5 shows the cross-sectional view of author's proposed sensor. The limitation of this proposed sensor is analyte field internally, plasmonic material coated internally, and that's why the fabrication process is more complex. Figure 6 is the conformal loss with respect to the wavelength at different temperature. Another literature review, Mr. Horn et al. Proposed a temperature sensor with sensitivity is 720 picometer per degree Celsius. He used gold as a plasmonic material. Figure 7 is the cross-sectional view of the author's proposed sensor. The limitation of this proposed sensor is some air holes internally coated with a thermo-optic coefficient, some air holes are selectively coated with metal, and that's why the fabrication challenge is huge. Figure 8 shows the conformal loss with respect to wavelength at different temperature. In Mohammad Farhat et al. Proposed a temperature sensor with sensitivity is 1.019 nanometer per degree Celsius. Gold nanowire is used as a plasmonic material. Figure 9 is the cross-sectional view of author's proposed sensor. The limitation of this proposed sensor is central air hole coated with a liquid crystal, plasmatic material infiltrated, and that's why the fabrication process is more complex. Figure 10 shows the conformal loss with respect to the wavelength at different temperature. The objectives. The main objectives of my thesis is increase the sensitivity with respect to wavelength, increase the performance, simple design, temperature sensing in remote place. This is the proposed model of my temperature sensor. The figure 11 is the cross-sectional view of my proposed sensor. The design parameter of my proposed sensor is thickness. The thickness of gold layer is 30 nanometer. The diameter of each air holes in a second ring, which indicates by A, is 1.2 micrometer. And the air hole in the first outer ring, which indicates by B, is 5 micrometer. The pitch, that means air hole to air hole distance, is 2.7 micrometer. Here we use the PDMS, polydimethyl, that means polydimethyl siloxane, as an analyte. This is the required formula, mathematical formula, which are used. Figure equation 2 shows the refractive index equation of fused silica. Fused silica is used in the background of our proposed sensor. Figure equation 3 is the refractive index equation with depending on the temperature. And equation 5, 6, 7, and 8 is the equation of our performance analysis. This is a simulation result. Figure 12 is the dispersion profile of proposed sensor. In this figure 12, we can see that at 850 nanometer, the real part of the effective core mode, the real part of effective mode of core mode and the SP mode are totally matched. This is the phase matching condition. At this wavelength, the maximum energy is transferred from the core mode to the SP mode. And figure 13 shows the optical field distribution of the proposed temperature sensor for core mode and SP mode. Figure 12 is the loss spectrum of proposed sensor. We simulated this result at 30 degrees Celsius, 60 degrees Celsius, and 90 degrees Celsius. Figure 15 is the loss spectrum of exposed light when the diameter of the air hole is increased 2.5%. Here also the simulation is performed at 30 degrees Celsius, 60 degrees Celsius, and 90 degrees Celsius. Figure 16 is the loss spectrum of exposed light when the diameter of air hole is decreased 2.5%, and figure 17 is the loss spectrum of exposed light when the thickness of gold layer is 40 nanometer. Figure 18 is the loss spectrum of exposed light when the pitch is 2.6 micrometer. All these simulations are performed at 30, 60, and 90 degrees Celsius. There are two simulation tools are used. One is COMSOL multipage software, and another one is MATLAB software. This is the working process. Figure 19 shows the working process diagram. First we design and simulation, then data collection, and then calculation, plotting, and performing analysis. This slide show the performance evaluation of proposed sensor. In this table, we see that at 60 degrees Celsius, our sensor sensitivity is 4.67 nanometer per degree Celsius. Resolution of the sensor is 2.143 into 10 to the power minus 2 degrees Celsius. Detection accuracy is 0.0125 per nanometer, and figure of merit, which indicates the quality of the sensor, that is 0.05838. This slide shows the performance comparison between the RAVE sensor and the previously reported sensor. In this table, we see that our introduced sensors, the detection range is 30 to 90 degrees Celsius, and sensitivity is 4.67 nanometer per degree Celsius. That's why we can say that our introduced sensor is more sensitive, more eligible, or more sensitive than other sensor. Conclusion: we can say that using gold as a sensing material, that's improve our performance, and use polydimethyl siloxane, which also helps our sensitivity, to increase the sensitivity of our sensor, and it's also a real life application. Future: fabricate the sensor and compare with a simulated result, and implement the graphene or silver layer with a gold layer to enhance the sensitivity. Figure 20 is the experimental setup of the proposed sensor. Here, this is the reference. This is the reference that we are used, and thank you all.